Hello calculus students, this is Mr. Fugay, and this video we are going to do a pre-calculus review of inverse trig functions. So this is going to be split up into a couple parts, first in terms of notation, graphs, and then how to evaluate. So let's go ahead and let's talk about notation first. So over here I have the trig function sine of x written out as y equals sine x. Now we could do this for the other five, but we're going to focus just on sine for this introductory part of the video. Now, as you know, to find an inverse, the quickest way to do that is to switch the x and the y variables. So the inverse trig function defined implicitly would be x equals sine of y. Now what we need to do with this is I want to try to define this explicitly, meaning to solve y and get y by itself. The inverse of sine is the inverse sine function, so we would take that from both sides, just as I'm doing here in red, and what we would end up with is the inverse sine of x equals y. Now this notation with the superscript of -1 is indeed a notation for the inverse trig function, but there is another one that you came across in pre-calculus, and this is the one we'll probably use more often. As opposed to writing sine raised to the negative first, we would use the arc sine function notation, and that means the exact same thing. So keep that in mind as we move forward in this review. Now let's talk about the domain and range. Because in the original function sine of x, we're going to have a domain of all real numbers. And then our range is going to be a closed interval from -1 to +1. So that's what we see at the function at the left. But as mentioned in class, in order to find an inverse, we need the function to be 1-to-1. In other words, we need the function to be monotonic. Exclusively, or I guess we should say, if it's only increasing and never decreases, or vice versa. So in this case, what we're going to have to do in order to even find the inverse is we have to restrict the domain. So the domain that is typically restricted here on the sine function is from its minimum value to its maximum value closest to the origin. So in this case, the part that I have here in blue is our brand new restricted domain. So to find the inverse, we're going to change this to be from -π/2 to π/2. And by restricting that domain, I have now made the function 1-to-1, which is why you see the graph below arc sine of x written in blue the way that it is. The domain and the range will switch positions. So now the domain will be from -1 to +1, and our range, which is now our truncated domain, is going to go from -π/2 to π/2. Now I want to just keep in mind for those of you that are thinking about the unit circle when we get to evaluation, -π/2 to π/2 is going to be quadrants 1 and quadrant 4 on that unit circle. And we're going to need that in just a few moments when we talk about evaluating. Now this process that I just walked you through in the first 3 minutes can be applied to all the other 5 trig functions. So what I want you to see below here is a screenshot from a textbook that shows you all 6 inverse trig functions. Now we've already gone over this one right here, and I showed you how that was built and developed. And notice once again that the range, our outputs, are going to be values that are in quadrant 1 and quadrant 4. But look at the other functions here, and again, using the same logic that I showed you, we could derive this. For the arc cosine function, we are going to restrict it to quadrants 1 and 2. For arctangent, it's going to be quadrants 1 and 4. And then moving down to our reciprocal trig functions, this is going to be restricted to quadrants 1 and 4, quadrants 1 and 2, and lastly quadrants, 1 and 2 again. Essentially, you are using one positive quadrant and one negative quadrant. What I mean by that is the sine function is positive in quadrant 1 and negative in quadrant 4. That's the reason that will work as a restriction. And the same thing can be said for the other 5 trig functions. And again, please reference any notes or work that you've done in pre-calculus that will help dig a little bit deeper into why we have to restrict this the way that we do. This will play a role when we start evaluating this in just a few moments. So let's go ahead and do just that. Let's evaluate some of these inverse trig functions. So we're going to start with letter A, the inverse cosine of 1/2. Now, one thing that might help sometimes when you're trying to think about this and what you're processing is that really what this is saying is that cosine of what angle is going to give me a ratio of 1/2. Now, you can use the unit circle for this, or we can use the 5 trig tools that you learned back in geometry and pre-calculus. And that's exactly how I'm going to phrase this. So I know that my 30, 60, 90 triangle has a 1 and a 2. And so the cosine of 60 is actually 1/2. That's better known as pi over 3 in the world of radians. Since the 1/2 is positive, we're going to look at our 4 quadrants, A, S, T, C. Quadrant 1 and quadrant 4 are going to be the 2 places where we would have a positive value. So the quadrant 1 answer would be pi over 3. Our quadrant 4 answer can either be written as 5 pi over 3, or you may want to get in the habit of just writing it as a negative radian instead, negative pi over 3. The inverse cosine function, let me go back up here, is restricted to just quadrants 1 and 2. So I am going to reject the quadrant 4 answer, and our solution for this is going to be pi over 3. So the inverse cosine of 1/2 is equal to pi over 3. Let's take that same principle and let's apply it to letter B. Now in this case, we're given that we're looking for arc sine of 0. Remember, that's the same thing as inverse sine of 0. In other words, I'm looking for when sine of x is going to be equal to 0. Now when we're using zeros, ones, and negative ones, typically that means it's going to be a quadrantal angle, meaning 0, pi over 2, pi, 3 pi over 2, and so on. So I'm going to look at the sine function. Look at this right here. This is the graph of sine. And we see that 0 would be here as well as here. But remember, so that's 0 and that's 2 pi. But remember, the domain of sine, as I showed you in the beginning of the video, is negative pi over 2 to pi over 2. So the answer we're going to reject is the 2 pi, and we're going to accept 0 as our answer here. Now this may be a good place for you to pause the video, and I want you to try letters C and D now and see if you can apply these principles to both of these problems. Now I'm going to go ahead and go over these regardless, so let's go ahead and let's talk about them. So once again, I'm going to view this as secant x equals negative 2 root 3 over 3. You can also view that rationalized fraction as negative 2 over root 3. I just like that personally better because it ties back into my triangle a little bit better. If we go to my 30, 60, 90 triangle, we will see secant is the reciprocal of cosine. So that is going to be 30 degrees, better known again in radians as pi over 6. When I look at my quadrants, secant is going to be negative as it's listed here in quadrants 2 and 3. We are only going to focus on the quadrant 2 answer because once again, the domain is restricted so that we would only get one output. So in this case, the answer that I'm looking for is 5 pi over 6. That's the quadrant 2 answer when reference angle is pi over 6. Okay, moving on to the cotangent. This is going to, again, I view this as cotangent x equals negative 1. Whenever tangent or cotangents equal to 1, I'm immediately thinking about my 45, 45, 90 triangle, also known as pi over 4. Just as we mentioned here, we're going to look at our 4 quadrants again. Tangent and cotangent are negative in quadrants 2 and 4. Now for the cotangent function, this is an important distinction that we need to make that can be a little bit confusing. You'll notice that cotangent is restricted to quadrants 1 and 2, and tangent is restricted to quadrants 1 and 4. This is very confusing, but the reason why this is done is to avert having a vertical asymptote in the middle of it. So that is one thing that is often forgotten, and I will agree that that is kind of the trickiest part of this, is remembering that we would actually accept the quadrant 2 answer in this situation, which is 3 pi over 4. So that's going to be my solution here. Okay, so for the last part of this video, we're going to look at a function composition of inverse trig functions and see how we would do here. Now, we're not going to do a lot of these in practice, but I want you to see how this works and understand how the domain restrictions that we talked about in the beginning of the video actually affect the answers. Because a lot of students will look at a problem like letter E, see the tangent and the inverse tangent and say, oh, they cancel each other out and the answer is 1. Here's where we need to be careful. Sometimes this is true and sometimes this is false. Let's talk about why. So let's go ahead and actually do this brute force. Inverse tangent of negative 1 is going to be equal to pi over 4, kind of using the same logic we just did with the cotangent problem just a moment ago. And when I evaluate tangent of pi over 4, well, I get 1 as an answer. So the assumption that we had just made in the previous as I began this problem, actually held true. The answer was indeed 1. Here's where we're going to actually see an issue, and that's going to be here on letter F. Arc sine of pi, our theory probably is that the answer here will be pi. But let's talk about why that's not going to be the case. If I go ahead and evaluate sine of pi, I'm going to get an answer of 0. That's going to be the output here. And then I'm going to be asked to find arc sine of 0. Now the issue here is that arc sine of 0 can be equal to 0, pi, 2 pi, and so on. But because of our domain restriction specifically being between negative pi over 2 to pi over 2, because of that restriction, the answer we're accepting here is 0. And so the answer to this problem is 0 and not pi. So when it comes to these compositions of inverses, it's usually best to just evaluate the function from the inside out and then keeping in mind of those restrictions that we've talked about when evaluating the problem. So there's 2 more for you to try here. We have an arc secant of a secant, and then finally a cosine of arc cosine. So go ahead and try these out, and then I'll go over them to wrap up this video. Okay, so as I've mentioned here, we're going to go ahead and evaluate this inner function first, and then we'll take the arc secant of it. Secant of negative pi over 4, that's a quadrant 4 value, reciprocal of cosine. That is going to give me a value of the square root of 2. And from there, we would then use the same kind of information we looked at before. So the square root of 2 lies in my 45, 45, 90 triangle. So pi over 4 is my reference angle. It is positive in quadrants 1 and 4. But for the secant function, we're only going to accept the quadrant 1 answer. And so the final solution to this is pi over 4. So you will notice that we did not get negative pi over 4. We got positive pi over 4. And that was due to the domain and range restrictions of these trig functions and their inverses. However, when we go to letter H, and we take the arc cosine of root 3 over 2, root 3 over 2 is going to be a 30-degree angle, so the solution to that is pi over 6. And then we will evaluate the cosine of pi over 6. Again, if you need help with that, there's your 30-degree angle. Root 3 over 2 is indeed going to be the answer for this. So the purpose of these last 4 examples is just to remind you of the importance of understanding the domain and range restrictions that we have to apply to the original trig functions as well as their inverses in order to make it one-to-one, aka monotonic. So keep that in mind as you move into the practice problems down here below. There are 6 of these for you to try. Make sure you feel comfortable with these before we move into class and start talking about how the calculus will embed with what we've talked about here. That will conclude this review video. Have an awesome rest of your day.